So now I'm going to tell you about one of the most popular ways of solving this system of equations. Again, this is probably something that you have done in linear algebra, but it gets used a lot in optimization as well, which is using the SVD. Okay, so many of you who have done linear algebra have not done SVD, so this will be a bit of a revision. Anyone here who has not solved this using SVD? Yeah, you can raise your hand. It's okay. I'm expecting most of you to raise your hand over here. Okay, good. So this is going to be fun because this is a really useful tool. Okay, so my matrix A over here. Every matrix has an SVD. That's the good news, right? So I'm going to write this as USV transpose. That's the singular value decomposition. This guy is M cross N. My input matrix is M cross N, right? For now, we'll keep it general. It could be tall, fat, square, whatever. What is U? M cross M. Something more about it? It's an orthogonal matrix. All the columns are orthogonal to each other, right? It forms, therefore, if they're orthogonal with respect to each other, what is the other nice property that you get out of it? It's a basis for Rm. Any vector in m dimensional space can be written as in terms of the U's. What about this guy? This guy therefore is size m cross n, and what are its properties? Diagonal, it's a diagonal matrix. It need not be square, but it's a diagonal matrix, and the diagonal entries are the singular values. Right? Similarly, this is n cross n, V, and V is also what? Orthogonal matrix. Okay, it's a n cross n orthogonal matrix. Therefore, we also have a nice basis for Rn. Right. So this is sigma I, and all the singular values, regardless of what the matrices are, what? Greater than equal to 0. There is never a negative singular value. Okay. So if it is a tall matrix, this is how S is going to be. This is m greater than n, and if m is less than n, then it's going to look like this. This is 0, this is 0. This is how the S matrix looks like. Okay, so now let's look at, this is the equation that we are trying to solve, A transpose AX. So let's look at A transpose. What is A transpose going to be? When we apply the transpose operation, everything flips around, right? ABC transpose becomes C transpose, B transpose, A transpose. So let's write down A transpose A. Okay. So A transpose, what is the first term I should write? V S transpose. Is there a reason, is there a need for me to put a transpose on S? Yes, because it's not square. Okay. Next comes U transpose, and now this is getting multiplied by USV transpose. Okay. Can this get simplified any further? U transpose U, identity. Okay. So this becomes V S S, sorry, S transpose S, right? S transpose S and V transpose. Okay. What will happen to S transpose S? It's going to be square, of course it's going to be square. Anything else that we can say about it? Diagonal element, it will be diagonal. Singular values. Singular values will be sitting on the diagonal as what? Sigma I squared. Right? So S transpose, what is the size of S transpose? N cross M. Now S transpose into S is going to be N cross N. Right? So this is N cross N. And that makes sense because V and V transpose anyway are N cross N. So everything, all the sizes are consistent, right? So that's one way of doing a, what they call a idiot check. Okay, so now we are looking at A transpose AX is equal to A transpose B. That was what I was trying to solve. Okay. Now let's plug in what we have done. So V S transpose S V transpose X is equal to I need to put this guy back in over here, A transpose. So that becomes V S U transpose into B. Say again, S transpose, correct, S transpose. Fine. So I've just substituted over here A transpose. This is my A transpose A. Okay. What can we do next to simplify this? There are a lot of extra terms over here, or some extra terms. What would you do? Remember, these are not scalars that I can just knock off 5 common on both sides, right? So, okay, one suggestion is left multiply by V inverse. V transpose is the sensible thing to do, right? Because for an orthogonal matrix, the inverse is the transpose, right? Okay, so left multiply by V transpose, that's going to give me S transpose S V transpose X is equal to S transpose U transpose V. Okay. Now question is this invertible? It depends, right? So first of all, what are they? So it's n cross n, right? S transpose S is n is square and size n cross n. The entries of this are what? Sigma I squared. I is equal to 1 to n, right? Now this is a tall if let us say if m is greater than n, or let us say greater than equal to n, okay? If it is full column rank, what does it mean for the singular values? All are non-zero right up to sigma n, right? If, okay, so if this is a tall matrix and full column rank, then sigma n is not equal to 0. In that case, this guy is invertible. Yeah. All right. Okay, so let's flip this guy around. I'm going to get V transpose X is equal to S transpose S inverse S transpose U transpose B. Okay. Can I still simplify it further? I am interested in X. Left multiply by V, so that V transpose goes away. So then I'm left with X is equal to V. Okay, so remember, you can see why full column rank is absolutely critical, because without that I cannot push this guy to the right hand side, I'm stuck, right? So full column rank is allowing me to write down X in a closed form expression. Is this term underlined over here, is it going to be something simple? Right, S transpose S inverse, it's a square matrix. What are the entries? 1 by sigma I squared. That's getting multiplied by S transpose. What will I be left with? 1 by sigma I kind of thing. But we have to do it a little carefully, because I'm multiplying a square matrix by a fact matrix. S transpose is now a fact matrix, right? Now, S transpose is something that looks a little bit like this guy. This S transpose looks a little bit like this, right? So I'm going to write this as this V remains as it is. This term underlined is what I'm going to call diagonal inverse, roughly 1 by sigma I, okay? And this, I'm going to write it in a little bit of a different notation. U1. Now, why am I calling this U1 is because this guy is like this, right? S transpose is like this fact. When it gets multiplied by U transpose, what will happen? I'm going to have a whole bunch of zeros get multiplied by the rightmost columns of this U transpose. So what I will be left with are the first n columns of U transpose. So this U1 is what I am calling as the matrix which is found by not first n columns of U. It's a U transpose. Okay, and then D inverse is just my 1 by sigma I. Okay. So here is my solution which has come from SVD. Simple manipulation of first n columns of U transpose. No, it should be of U. So let's have a look at this. So these are the columns of V, V1 up to Vn. Okay. Diagonal. So this is going to be 1 by sigma 1 up to 1 by sigma n. Okay. And then I have something like this. That's what is going on over here. Okay. You can also write this, you can open this up in terms of what is very popularly called as the outer product notation, which will make it very, very simple. So let's write that down over here. N is equal to 1 to n. This 1 by sigma is a scalar, it is going to pop out 1 by sigma I. Okay. Ui is going to get Ui transpose is getting multiplied by B. Okay, so before I write this, let's just get some intuition. Let's start from the rightmost side. I have a whole bunch of row vectors that are getting multiplied by B. Those are going to form scalars. Those scalars are then getting multiplied by V, right? So imagine if this whole thing over here should boil down to what? A scalar, a vector, or a matrix? It should boil down to a column vector. Once I get a column vector, that's getting multiplied by a matrix V. So in terms of linear combination, how am I interpreting this? X is a linear combination of the V's with some coefficients. Now all we are trying to do is interpret what those coefficients are. So I'm going to get 1 by sigma I is obviously going to be there, and you notice this is going to be Ui transpose into B. Okay. This is my coefficient, and that's simply getting multiplied by Vi. So this is my solution to the least squares. This is like the ideal textbook solution that starts with the SVD, you work it through, and you end up like this. Okay, this turns out is hiding a lot of important points over here, which from a numerical point of view will make or break your solution. So now let's have a look at that. I've written n over here because we said that the matrix had full column rank. Okay, so now let's make things a little bit more interesting. This summation over here, I can write it in a way. Let's make things a little bit more realistic. In this entire setup, Ax equal to B, where is noise appearing? B, right? Because my A into X was my linear model, right? X1 plus X1 multiplied by X2 multiplied by T, whatever, right? That's the model part. B is where I make a measurement, and that measurement can have some noise. So if I had noise in my measurements, who is the most dangerous guy? Sigma 1 or sigma n? I hear one sigma n. Anybody else? Anybody else? So where is the noise sitting now? The noise is hiding in this guy, right? So who's the most dangerous guy? Who? Sigmas are always in decreasing order. Sigma 1 is highest, sigma n is smallest. Sigma n, right? Because sigma n is the smallest guy and it's in the denominator, right? So the way to see this is I can just write this as I is equal to 1 to n minus 1, 1 by sigma I ui transpose b. This is the coefficient multiplied by vi plus 1 by sigma n un transpose b vn. So let us say that my condition number kappa was 10 to the 4, let us say, and sigma 1 was 1. Therefore, sigma n is how much? 10 to the minus 4. This is my condition number. This is a reasonable condition number. It's not something very bad, right? So what is going to happen now in this term? 1 by sigma n, 10 to the 4, and of b I can write it as b naught plus some noise, right? This noise is inside b, you never have access to it separately. The b is a noisy measurement over there. It has some true value and some measurement, and you can never split the two. You get it as a wholesale deal. So you notice what will happen now? This b which I have written as b naught plus delta, that delta is getting multiplied by 1 by sigma n, which is 10 to the 4. So, okay, so that's one noise term. And on the other hand, look at the higher singular values which you were so happy about. Sigma 1 was 1. That's forming the first half of the solution. The first part of the summation, 1 by sigma 1, 1 by 1, no problem, 1 by something something, right? But it is competing against 10 to the 4 into the noise. So this noise over here in the solution is going to swamp your true solution. Okay, so when you write, this is one of the major advantages of writing the solution using the SVD. You can immediately see which is the guy who's going to corrupt your solution the most. The smallest singular values are the ones that are going to corrupt, give you the maximum error in your solution. If you had done, for example, Gaussian elimination or Cholesky, whatever, you wouldn't be able to see, oh, this is what is happening, right? So, I mean, there are of course many strategies over here. Supposing you are in charge of controlling the errors, what would you do? Simplest strategy is let us knock off the lowest singular values, meaning I exclude them from the solution. So, it's a very, very popular technique in engineering, and the name for it, therefore, you can guess, truncated SVD. That's where the phrase idea comes from. That if I have some singular values which are very low, they're going to amplify the error. Rather than face that error, I get rid of it. There is going to be some inaccuracy now that is coming, right? So, reduce error by here I gave you the example of just the highest, I mean sigma n being very small, but you could have the last several set of singular values could be very bad. So that's why truncated does not mean just one. You could truncate it by a few terms, right? So this would, then you would write this as I is equal to 1 to r 1 by sigma I ui transpose b vi. Okay. So this is my x star. By the way, this solution which I wrote over here is goes by another very common name in the literature. Does anyone want to guess what this solution is called? It's called the pseudo-inverse. It's called the pseudo-inverse because it's not a square matrix that I inverted, therefore it's not the inverse, but it has properties that are almost as good as the inverse because I basically minimized Ax minus b. So this is also called the pseudo-inverse, and this is our truncated SVD. So from a linear algebra point of view, can you comment on what happened over here? The hint is that we said that x is an n-dimensional vector, therefore I should be able to express it in the basis of which u or v? V, right? Any vector should be expressed as a linear combination of my n basis vectors. My original solution did it have all n basis vectors? The pseudo-inverse? It had it. The truncated solution, however, does it live in the same space? No, right? So as error is coming, the singular values which are lowest in magnitude are corrupting that part of the subspace which is corresponding to the highest singular index, right, sigma n. So you notice that this guy, this truncated solution, has no components of x along Vn. And if I truncate more, it will have nothing along Vn minus 1, right? So that is how it is. So there are tricks and techniques in signal processing where what they will do is, you say that I know that there are certain dimensions, for example Vn, Vn minus 1, Vn minus 2, where I dare not use my data. If I use my data, my error is going to blow it up. So I don't estimate that part of the solution from the data. I estimate that part of the solution using some a priori information about the problem. This is where things like compressive sensing and all of these ideas come from. So what can be determined from data, you nail it down using the truncated SVD. What is left, you use your other information about the problem. For example, I may, and this is a very real life example, I may say that the solution is sparse in the DFT domain, right? Natural images, for example, if you take image of a dog, cat or whatever and take its DFT and look at the coefficients, you will find out most of the coefficients are actually 0. It's just a property of natural images. But if you look at it in the pixel domain, it's a full image. There's nothing that you can discard. If I start dropping out some pixels, you can see this is a pixelated image. On the other hand, take its DFT and look at its coefficients. You will find out that a large number of coefficients are actually very low in magnitude. If you set them to 0 and then take the inverse DFT, the image looks almost the same. And this is at the heart of, in a very crude way, at the heart of JPEG and all, that you can get rid of information like this without losing the picture quality. So I get some solution. Now supposing I transform it into the DFT and I try to reduce the coefficients. That's how I can set these extra Vn, Vn minus 1, in some way. So these are the kind of tricks and techniques people will use in signal processing, image processing and so on. But having this idea of the singular vectors and what noise is doing to what, then you are in command of the situation. Okay, these dimensions are fine. For example, V1, V2 are fine. Noise is not going to bother me. Vn, Vn minus 1 is going to be dangerous. Let me not let noise predict that part of the solution. So this is how you can, and keep this in mind when you look at your course project papers. You will find tricks like this being played all the time. Okay. Any other questions on this truncated SVD or SVD in general, for those of you who saw SVD for the SVD solution for the first time? Another way in which you find this expression which I have written over here, Ui transpose B, is it a scalar or a vector? It's a scalar. Vi is obviously a vector. Can I rearrange the order of scalar and vector? Who cares, right? So I could also write this as 1 by sigma I Vi Ui transpose B. Everyone agrees? Does this bracket have any real meaning, or can I skip writing that bracket altogether? I can skip it. So I can also write it like this. Now can I reinterpret this? Can I put a bracket like this now? Is it legal? It's perfectly legal. Now what is the meaning of this now? So I've written my solution is I is equal to 1 to r, x is equal to this. What is the meaning of this thing that I've written now? It's a sum of rank 1 matrices, because Vi Ui transpose, Vi is a column vector, Ui transpose is a row vector, its product is a n cross n matrix, but it's a matrix of rank 1. How many such rank 1 matrices are there? R. So I've written my solution, this is another very nice interpretation. I've written my solution as the sum of R 1 rank matrices. Without, I've just changed the brackets around and I've got this one rank 1 approximations going on over here. So there are, for example, there are all of these rating problems, right? Netflix rating, that if you a user has ranked these movies, can you guess what are the ratings that he or she would give to movies which they have not seen? So in these kind of problems, it ends up being a problem of completing a unknown matrix. I have some entries known and some entries unknown. Many times that is written in terms of a minimum rank expansion of a matrix. So tricks like this help you over here. If you wanted to write the x in terms of least number of rank 1 solutions, here is it's sitting over here. Here there are r rank 1. If you wanted to reduce it to make it just 1, you just put r equal to 1. Okay. So this sounded vague, but go look up ratings problems and matrix completion problems. So this idea of using rank 1 matrices comes from here. Full rank. Yeah, which was the pseudo-inverse. Yeah, this was the A has full column rank. This gave us the solution x star is equal to this. Yeah. For the normal problem, not Ax equal, well, yeah, you could call it for Ax equal to B also. Yeah. Okay. That is, yeah, that is not invertible. I mean, then what happens is that S transpose S is not invertible, right? I agree with you. So what you could do instead is this. So it's a defective kind of a solution, but you know, in engineering problems, you are desperate. You want a solution which is somewhat close to what you want. So this is what you can do. Well, if it is rank deficient, it will satisfy. If you keep aside the error part of it, of the highest singular values. Actually, let's try that out. You can try that out. Take this, supposing A is not full rank, take this solution and plug it into the normal equation and just see, does it satisfy? Sigma will get multiplied by, yes.